Yeah, it's good.
Okay, yeah, so I'm happy to introduce Umut Shimshekli. Umut is the research faculty at the INRIA Sierra team and École Normale Supérieure. And his research is mathematical machine learning using a wide array of mathematical tools, like, for example, stochastic calculus, statistical learning theory, and Hausdorff dimension.
Sorry, so I'm struggling here. Go back.
No worries. And before his scientific career, he had a previous life as a successful bass player. It's good to know about Umut. So the floor is yours.
Thank you. Could you please let me know like 10 minutes before?
Yeah.
Because, okay, so, well, thanks a lot for organizing this event. It's amazing. This is here officer, so I'm super happy to be here. And today I'm going to talk about, like, thanks to the author, like he said, the like notation and everything. I'm going to build upon the framework of like Heritial stochastic differential equations, their use in machine learning, and their properties that we can try to understand. So this is going to be the topic of this talk, and it's going to be, if I can manage to make this work. Why is this not working? Okay, maybe I should give up.
Oh, did you plug the USB?
Yeah. No, it worked in a weird.
No, you have to switch it up. What is on?
No. I mean, it works in an unexpected way, like God. If you So I give up. All right. Also, this doesn't work. So maybe this is. Wait, sorry. Can you like not count this time from my?
Sure. Yeah. We can like everybody just gets coffee when they want to, and we'll eat the coffee break.
Okay, fine, it's working. All right. So this is going to be like the talk is going to contain like 5 years of research. So I'm going to talk about each of these like parts in a very short amount. So it's going to be like a teaser if you want. And my goal is to create some like discussions after the presentation. So I'm going to skip a lot of detail. I'm going to try to give you like the most important ideas, and then hopefully this will create some interesting conversation tonight at the beer garden. So to set the notation, so we are interested in general, I'm interested in deep learning, but in general, like in statistical learning theory, we are interested in minimizing a population risk, which is an expectation of a loss function. So we are parameterizing some, we have a parametric model, which is parameterized by some W, which lives in RD. And our goal is to minimize this expected loss, but in practice, we don't have the expectation is taken over the data distribution, which is typically unknown. And we cannot really use this optimization objective to operate. So in practice, we resort to empirical risk minimization, where we assume that we have a data set of endpoints. And instead of trying to minimize the true expectation over the data distribution, we replace this by the empirical expectation, which is taken over the empirical measure over Z1 to Zn. And then this R hat is called the empirical risk. And this is actually like trying to minimize this thing. It's actually what we do in machine learning and what we call training. And to attack this optimization problem, even though this can be very, very complicated in a neural network setting, because this function is not going to be convex at all, it's going to be horribly non-convex. Even though this is the case, practitioners use like very simple algorithms, for instance, the stochastic gradient descent algorithm, which is, just to set the notation, I know it's the same thing over and over again, which uses a very simple recursion, which is like to obtain the next iterate, we use the previous iterate minus a step size times the stochastic gradient. And the stochastic gradient is just obtained as the average of some randomly chosen data points. I mean, like the gradient evaluated randomly chosen data points at every iteration. So this is the setup. And in learning theory, what we are interested in is that, okay, so let's say you have some data set and then you train some neural network on your training sample training data set. But what you are really interested in is not the empirical risk, which is this R hat, but you are really interested in the true risk that is that this neural network is giving to you. So the true risk essentially can be thought of the test error. So because it contains the information about like all the unseen data as well. And this is what we are interested in. And we want to estimate this quantity. So there are many different ways of trying to get an estimate of this on this quantity. So one potentially practical approach is based on this very simple decomposition. So we are saying that the true risk is smaller than the empirical risk plus the difference between the empirical risk and the true risk. So this second term is called the generalization error because we are saying that if these two terms are similar to each other, my neural network is going to generalize to unknown data points. And the good thing about this decomposition is that now, since I have access to the training data points, I can compute this quantity. And if I have a computable error, like upper bound on this quantity, then I can combine these two and then try to get an estimate for my test error. So this is the goal. So in learning theory, this has been a very long-standing topic. And like there have been, there are like many different groups trying to get nice upper bounds on this generalization error. So to give you like a glimpse of the state of the art right now, I want to give you an example from a paper from 2017. So here, what the authors do is on the left, we have a real neural network. And then what we do is so for each point, we train the neural network. And then we compute after the training, we compute the training error and the test error. Test error means I compute the error on some unseen data points. And then I repeat this procedure by increasing the number of parameters in the neural network. And then we see that, obviously the training error is going to go down because I'm using a more powerful, more expressive neural network. But then the surprising part is that the test error also goes down and then it just stops over here. So this is completely contradictory to the traditional learning theoretical results, which say that if you are increasing the complexity of your model, at some point the test error should increase, and then you shouldn't be able to see something like this. And if you look at the upper bounds on the generalization error, which are called the generalization bounds, they are usually, not usually, they are always increasing with the number of parameters, which essentially indicate that you shouldn't use more parameters. So you should use less parameters as much as possible, but then the practice is not saying that at all. And then there's a huge gap between theory and practice. So, okay, what could be, and also another situation is that, so let's say you have a neural network, you have stochastic gradient descent algorithm. You run the training algorithm with some step size or learning rate, and then you obtain a neural network, and then you compute the test error. And then you repeat the same procedure by using a different learning rate. And then you obtain another neural network with pretty much the same training error. So they get very low training error. But then when you compute the test error, they can be completely different. So this means that by changing the hyperparameter, which is the step size of the algorithm, you can obtain two neural networks where the empirical risk is the same, but then the true risk is not the same. So the algorithm is finding different places. So this is also not, this cannot be explained by the existing learning theoretical results. So then, what is the context? So the problem with most generalization bounds is that they usually discard the effect of the chosen data set. The algorithm itself, so because I could use stochastic gradient descent, I could use a different optimization algorithm, the choice of the algorithm, and the choice of the hyperparameters of the algorithm. So these things are not really used in the existing generalization bounds, and this is a problem. And the main goal right now in learning theory is to incorporate all these things into the generalization bound and try to get something more interesting. So this is the context, and I'm going to connect this to the previous talk, Ofir's talk, where heavy tails are going to play an important role. So in this slide, I want to show you an empirical result from 2019 from a paper from Martin and Mahoney, where they show that, so they train a neural network and the parameters of the neural network are usually matrices, right? So you have different matrices at different layers. So what they compute is that so W is a layer matrix. So as you can see it as a parameter vector in a matrix form. So they compute W transpose W, and then they look at their eigenvalue distribution. And then they realize there is some sort of a heavy tail behavior in the eigenvalue distribution. And then this is a little bit heuristic. So they fit a power law distribution to this. And then they realize that, they empirically show that actually, and the exponent of this power law distribution correlates almost perfectly with the test error. So this means that if your matrix has some sort of like a heavy tail power law, heavy tail distribution of the eigenvalues, as it gets more heavy tailed, you are going to get a better generalization performance. And then this is quite, I don't know, surprising. So I wanted to see what's happening. And also, as what we mentioned, like I was working on like trying to understand the heavy tail behavior of stochastic gradient noise. And I wanted to see if there is any connection between heavy tails and generalization error in a mathematically rigorous way. Yes.
Are the parameters between 0 and 2 test error accuracy can be anything? So how they can be related?
I mean,
on one large scale.
It's a great question. So the aim of this plot is to show that there can be a relation. So maybe it could be alpha times 100 over x. I don't know. It can be a different thing. But like the goal is to show there might be some things between it. Yes.
Good question. You are looking for tuning on the right plot. Like is it for the singular number?
This is tuned, yes.
Okay.
Yes. Okay. All right. Okay, now I'm going to dive into the theorem directly because I have like 3 things to talk about. I hope I will be able to cover all of them. So as before, we have a data space Z, which is a product of features and labels. So this can be like images. This can be like if the image contains a dog or a cat, something like that. And again, like we have a training set of n elements. And now I'm going to assume that I have a training algorithm, A, which takes input the data set and it contains some algorithmic randomness, which is encapsulated by some random variable U. And the algorithm outputs a trajectory, like a continuous time trajectory, and the time is indexed by T, which takes values 0 and 1. So for instance, what I mean by this, I mean, like what I'm really interested in is actually this. So let's say you have, okay, so this is your landscape, loss landscape. So your algorithm is going near like some local minimum. And what I'm interested in, the behavior of the algorithm around this local minimum. So this is what I call by like this trajectory. So I imagine the algorithm is already next, like near a local minimum, and then I'm interested in the trajectory that the algorithm does near the local minimum. And I'm hoping that by just looking at this, it is going to capture the effects of the data because like the dynamics itself is depending on the data. It's going to capture the effects of the algorithm choice. So the dynamics is determined by that. And it's going to capture the effects of the hyperparameters as well. So this is why I'm trying to look at the trajectory near the local optimum.
So, could you really, I mean, when it's something you think there are more parameters. So, I mean, when the system has, let's say, like all the data, so you stop the learn. So, you can think that there's a kind of manifold of zero training loss in the system is modeling to create. So, it's not really more close to the.
Yeah, I'm not assuming there will be zero training loss. There can be zero, like 100% classification accuracy, but the training loss I'm going to assume is not real because otherwise it will stop. So I'm going to assume that even near local minimum is going to move a little bit, but the loss is usually something else. It's not the accuracy, so it might not stop. And actually, for gross entropy loss, it never stops. Okay. And then I'm going to use as the algorithm this stochastic differential equation, which has 3 parts. So it has a gradient flow part. So I'm trying to minimize the function f. So keep in mind f might be different than the empirical risk. I'm assuming there will be some Brownian term which will accommodate for the Gaussian noise. And then I'm going to assume there will be some heavy tail noise coming from some alpha stable process. Yes.
Question. So in other formulations for FD to actually the step side beta appears, does it also appear?
I mean, you can put it in the matrix.
Okay, all right.
Okay, so I'm going to choose this as my algorithm. And yeah, so this is going to be my setup. But the thing is, I'm going to assume there is a loss function, like my loss function is uniformly bounded. It is Lipschitz. But I'm going to use a different, I'm going to make this framework flexible enough that I can use a different function to minimize here and then different function to measure my generalization error because I will have different set of assumptions. But you can choose them as the same thing for this one, for this framework. And as before, I'm defining the true risk as the expectation of this loss function. And then I'm defining the empirical risk as the empirical average over of the loss function over the data points. And I'm interested in the difference between these two for the case of the stochastic differential equation. Is it clear the setup? Any question? Yes.
So how is the dependence on the parameter and the aggregate noise there? As you have this learning process, how is that because then
You mean like this?
yeah.
We let this to depend on it, but we don't specify anything about it. We just need this to be larger than 1. But in the experiments, we put some more assumptions to estimate actually. But let's keep this as a discussion topic. Okay. Because it's a bit more detailed.
What's the relationship between sigma 1s and sigma 1 and sigma 2s?
So we leave them like quite general actually. So we don't really care what's happening in the. Okay, so they can be very general, but what I'm going to assume is so let's say the algorithm. So this is not only for the behavior around the local minimum. So I'm just saying this is my algorithm, but I'm going to assume that near the local minimum, this is going to vanish. So like sigma 1 is going to be equal to 0, like near the local minimum. So I will only end up with this heavy tail node. So this is the only assumption that I'm making. But in the general case, like when the algorithm is not near the local minimum, I will allow there can be some gradient.
But for practical realization, how do we choose this sigma 1, sigma 2? Have a particular example.
So this is the part where I completely skip because like this is a model for what SGD is doing. Okay, so I'm not saying this is a rigorous thing of the SGD is modeling. Okay, so but I have a good argument. Don't get me wrong. But there is no right now theoretical result saying that if you do take up for the limit, SGD conversion doesn't exist. But I can claim that this can be a good model for the specific case. All right. Any other question? Yes.
Why is the generalizability idea a question about the algorithm? It seems to me much more a question about the function. Because I have in my head at the moment, just on the line, near the origin, and the function could be sine x, it could be x, it could be sinh x. And I've explored it at the origin, and I've got my training data, and then my testing data is a lot further out. And so I don't see how that error is to do with my algorithm. I see that the error is to do with whether I put sinh x, sine x, or x.
Well, the first thing is we are assuming the data is IID. So this data set cannot be too much different than the training data. So this is a fundamental assumption that we make, which enables us to relate these two quantities actually. And the second thing is, by using this, I'm actually trying to monitor the evolution of the function that I'm learning, because like each of these W's is essentially corresponding to a function that I'm learning. So it is not the W, but it's the function that I'm interested in actually. But since it's the parametric function, W plays an important role.
Yes. One more question. What is your signal? Why are your signals not depending on the time explicitly, but only on W?
So this is usually like this type of models are usually used in machine learning to express stochastic gradient descent. It is more like a convention, but we can put like a time t here. But like for our sake, these are not going to have any effect actually. So we can just choose them. However, I'm going to be interested in some. You will see, but like this is not going to play a crucial role. Okay, let's move on. This one? Yes. Okay, now I'm going to try to bound this generalization error, the difference between empirical risk and the true risk, by using tools from geometric measure theory and fractal geometry. So now let's start with the question. So who knows the Sierpinski triangle? Okay, so now the question is not for you. So what did, like, for the ones who don't know it, what is the dimension of this object? Is it 1-dimensional, 2-dimensional, 0-dimensional? infinite dimensional, isn't it? I mean, okay, so if you compute the area of this two-dimensional vector, it's 0. So it would be absurd to say a two-dimensional object. I mean, cannot be two-dimensional because area is 0. So then it must be 1, but it also doesn't make sense because if you compute the one-dimensional vector, it's infinite. So then you can define some like intermediate, like different notions of fractal dimensions, like dimensions, which are usually called fractal dimensions. Then like there are like different types of it, and there are like Hausdorff dimension, Minkowski dimension, technical dimension, different sorts. And then if you compute the Hausdorff dimension, for instance, for this object, it's going to give you a number between 1 and 2. So it is like a fractional value. So I'm not going to define what this is. Again, like it could be a topic for night. And the more interesting part is that so Markov processes generate fractals because fractals are usually generated by using some like recursions. And then the Hausdorff dimension that are generated, the Hausdorff dimension of the fractals that are generated by Markov processes are usually related to the tail behavior of this Markov process. So let me show you an example. So I'm showing like 3 stable processes with different tail indices alpha. So alpha equals 2 means it's a Brownian motion, and then I'm decreasing alpha. The process becomes heavier tailed as I go to the right. And the darker color means the time is 0, and as it gets lighter, time is increasing. So it looks something like this. And what I do is that, okay, now like this is a process in 2D. I am completely like dropping the time information, and I'm collecting all the points that are traversed by this process into the same set. Okay, so I'm putting everything in the same bag. And then they look like this. So this is called the image of the process. So if you think the process is a random function from time to space, this is the image of the function. And now, like, even though like there are the number of the points is the same for each of these plots, as we can see, like the topological structure is like completely different for each of these processes. So as we can see, as the tails get heavier and alpha gets smaller, the process gets a bit more simple. And actually, you can quantify this. In 1960, it was like shown that the Hausdorff dimension of these images are exactly equal to alpha, almost surely, where alpha is the tail exponent of this process. So this means that if you change the tail structure of the process, its topological structure is going to change as well. And then you can exactly quantify what is changing, and the dimension is getting decreased as you make the process severe tail. So this is going to be the main observation in the first generalization bound. All right, so the first bound. First of all, I'm defining a set that I'm interested in. I'm putting all the points that are traversed by my algorithm around the local minimum. So this thing. So I'm calling it WS, and I'm saying WS because it depends on the data set S. So this is important. So the first bound says this, so I simplified it quite a lot. So there are a lot of assumptions. So the worst case error that I'm going to do on the trajectory around the local minimum is going to depend on mainly 2 terms. The first term is the Hausdorff dimension of this trajectory, like the image, the set. And the second term is a coefficient called M, which is upper bounded by the mutual information between this trajectory and the data set itself. So it means that if this term is small, if the dependence between my trajectory around the local minimum and data set is low. So if they are not statistically dependent on each other too much, then this term is going to be low. And then this says that the fractal dimension of the hypothesis set, this set is going to be this main crucial term. It's going to dominate the other term maybe because of this low value. Yes.
No, good. Well, all the discussion of fractal dimensions makes sense for continuous time. In machine learning, you do it step by step, so you have just a set of individual points. So,
another beautiful. I have like a lot of things to respond to this, but this will get it off of this. So you can define fractal, you can identify some set which arise from discrete recursions as well, and then you can relate the generalization here to their fractal properties. So it is called the iterative function system. If you are familiar with it. All right, yes.
Is this based on the Rademacher bounds or?
It is not based on Rademacher bounds, but you can do related to the Rademacher bounds too. So it is directly a covering algorithm, a covering argument.
Okay.
But if you first go, I mean, like since this term is depending on S, the Rademacher arguments break essentially because like your function class depends on the data set. So this is why we directly do some like covering argument and then some decoupling by using the switching information.
But they also, I think this fact-based bounds what they have on the right-hand side is the sum of the gradients that you did. I think there's a couple of ways to derive the sort of results. I wonder how that relates here because there's also a notion of somehow a little bit what you visited in the space.
Well, I'm not really sure if they are strictly connected actually, but this is more like a topological.
Yeah, it's a little bit different, but it's still this notion of what you visited, right? This is what the WS is. So it's, yeah, I mean, if you connect them.
I mean, yeah, we can take a look. I'm not extremely sure if there is a one-to-one match.
Okay.
Yes, exactly. So, and then, I mean, there's a metric entropy argument, and then with further assumption, we link it to the Hausdorff dimension. Exactly. Any other question? All right. So, first observation, the Hausdorff dimension is always smaller than the ambient dimension D by definition. And then, so if we don't think about this second term, this Hausdorff dimension is telling us what is important is not the number of parameters, it is the intrinsic dimensionality of your algorithm actually around the local minimum. So if you go back to the initial complaint that I was doing, so the generalization bounds increase with dimension. So there is at least potential for this bound that it's not going to increase with the dimension, assuming like this term is not going to be like super crazy. Yes.
Can I, it's a very simple question, sorry for interrupting. What happens if you don't have motion? What do you get in this time?
So this becomes one, this becomes infinite.
This becomes infinite.
Yes. So it is not a good bound.
Okay.
In the case of noises setting. All right. Okay, now it is getting more interesting. If I choose my algorithm now, so like I chose the like this WS based on the algorithm. As the stochastic differential equation that I chose in the previous slide, there's a theorem from René Schilling saying that this is super simplified. The Hausdorff dimension is going to be upper bounded by the tail index around this point, around the local minimum. So with a lot of assumptions, etc. But then this essentially means that you can upper bound this term further by using the alpha that I was showing in the previous slides. And then you can get an explicit bound under further assumption, which is an alpha in the bound. Any questions? Okay, so this is the first result. So this says that, well, okay, I'm going to come back to the summary actually. 10 minutes, including this. I'm going to skip this slide. So we can apply the same argument for stochastic differential equations with fractional Brownian motion. And then this says that the Hausdorff dimension is going to be smaller than 1 over h. So Antonio was arguing that let's take h to 0. So this means, I mean, our theory says that Antonio's algorithm should not work. So this is a problem. And then this is both of us very sad. So, and I cannot really see how to reconcile these two things, but maybe it would be a good topic to talk. Okay, so this is like a small parenthesis. Okay, so what I've shown so far, we have a bound, the worst case bound, the worst case around this like trajectory, you have the tail index, and you have a mutual information. So here, like we have the tail index, it says that if the tails are heavier, if alpha is smaller, the bound is going to get better and better. But then we did some more experimentation, and then we saw that actually, like the behavior with respect to the tail is not monotonic. So, like if you like have like super heavy tail result, like algorithm, and then you might be degrading your performance. And then we try to understand how this is possible and why this is happening. So now I'm going to show you the second direction, which is algorithmic stability. One slide about algorithmic stability. This is a definition. We say that if we say that an algorithm A is stable, if when I run it on the data set S, and if I run it on some data set S set, where S and S set are almost the same data set, but they only differ one element. So I'm taking the same data set, changing one point in the data set. And I'm looking at the expected difference between the losses. And if this is smaller than epsilon, I'm going to say the algorithm is stable with epsilon stability. So again, like the idea is like if I change one point in my data set, the algorithm should not be giving like completely irrelevant outputs. So this is the thing. And the theorem says that if the algorithm satisfies this property, the expected generalization error is going to be smaller than epsilon. So it's a very simple theorem. Okay, now my goal is to see if I approach the problem of the Savitil stochastic differential equations from this point of view, can I get something more interesting? So I will just show you the quadratic loss. We also have some results for the non-convex loss, but this is pretty much the same idea. So let's say we have two data sets. The data set contains n elements. And then I consider the same data set, but I change only one element, the I element. And I'm right now, like for this sake of notation, I'm concatenating all these points and obtaining a matrix. And I'm considering two different stochastic differential equations, which essentially comes from like a quadratic loss. So this is going to be the gradient of the quadratic loss that we are considering. And here we are considering a non-state dependent diffusion coefficient. All right, so this is a very simplistic model with this specific case of quadratic optimization. So what we show that if you measure the stability by using a surrogate loss, not the quadratic loss that you are using, but some surrogate loss W transpose times data to the power P, where P is smaller than alpha. Alpha is the tail index. And if you assume the data is bounded and the covariance matrix has the smallest singular value, sigma min, the algorithm is going to be stable with this stability bound. So this stability bound is not important. What the terms are, if you are seeing, is not really interesting. What is more interesting is that there exists an alpha zero such that if your covariance matrix satisfies some property, this bound is going to be non-monotonic. So essentially, it will look like this. So if all these assumptions are satisfied, the generalization error alpha will look like this, and there is an alpha zero. So it says that okay, now by using this bound, at least for this quadratic case, we can see that there might be some non-monotonic relationship between alpha and the generalization error, and then this is coming from this direction. And I'm not going to talk more about this. Any questions about this? Because I want to mention the last part very quickly. Okay. So we do the same thing for the non-convex loss, but I'm going to skip. So it's pretty much the same story, but then the function class can be much more general. All right. So the last part, I think it will be really interesting. This is a very recent result, like a couple of weeks old. So this time I'm going to consider a very specific setup. One hidden layer neural network, where the second layer is fixed to 1 over n. I think Etienne was asking this question. And we have an activation function H, and then we are defining this is just the usual neural network definition with one hidden layer. And by using this function, we will try to predict the labels of the features y. Okay, so we are defining a loss function, which is going to measure the discrepancy between my predictions and the true labels. And I'm going to consider this algorithm. So as before, I'm having like a stochastic differential equation driven by some alpha stable process. Here, like this a bit abuse of notation because WT is a matrix, but you can think about this as SD over like the vectorized form of this. And actually, I'm going to consider the Euler discretization of this stochastic differential equation. Okay, so now the approach is compressibility. And then what do I mean by compressibility? So let's say you train the algorithm by simulating this process, and at some point you stop, and then you say that I'm going to compute the norms of each column of the parameter matrix that I learned, and I'm only going to keep some proportion of it. So let's say we fix a number kappa between 0 and 1. Let's say kappa is 0.1. I'm only going to keep the 10% of the columns with the largest node. And then I'm going to set all the other columns to 0. So I'm pruning all the columns, okay? So this is the setup. And I'm going to denote the pruned matrix as Wm kappa times m. So kappa times m is essentially indicating the coefficient. So this is the last results. The first result says that for any fixed time, for any fixed compression ratio kappa, so you fix it in advance, if your step size is small enough, there exists a level of overparameterization, like there exists a number of neurons, such that if your neural network contains more neurons than that, with high probability, the relative error between the true matrix that you learned and the compressed version is going to be arbitrarily small. So by adding this heavy-tailed noise, you essentially, if you are like over-parameterized and if you're increasing the number of neurons, you are going to obtain compressibility without making any efforts. It's going to be compressible by itself. So this is quite surprising. It uses some arguments from like propagation of chaos. And then by using this, you can immediately show that the generalization error is going to be bounded and it is going to be governed by this value kappa. So kappa is the compression value. So if it is more compressible, you are going to get a lower generalization gap. So this essentially says that if you are heavy-tailed and if you are using a neural network with like enough parameters, you are going to be compressible, and then it's going to. The number of parameters is not going to matter. What is going to matter is the number of compressed parameters. All right. So to conclude, the take-home messages: the tail behavior has strong connection to generalization error. In the first direction, we showed that the heavy tails will have smaller fractal dimension and they are going to cause a lower error. The second direction says the good level of heavy tails is going to give us better stability, which is going to give lower error. And the third direction is saying that if you are using a neural network with over-parameterization and plus heavy tails, it's going to cause compression, and again, this is going to give you lower error. So these are all aspects of the generalization error, but the open question right now is like, what is the effect on training loss? Because we never talked about it. So if the algorithm is heavy tail, maybe you are exploding your empirical risk. And the true risk is bounded by the empirical risk plus the generalization error. So that we also need to understand how this behaves. Okay, so sorry about like pressing the time. Thank you for your attention. I will be able to take questions.
And where's Dorian? Maybe Dorian can already come up to set up. Cool. And we can take one question in the meantime. Opia, I guess, or like Giulio, doesn't matter.
Can you say something about where does it come from? Where the data come from? So you didn't tell us. So can you say where the state come from? The data, what in the gradient and in the W. And so we didn't discuss the data actually. How much is, I mean, for example, the correct matrix of the data, you already scale the text there, so it is.
Stop the recording and restart it.
My understanding is there are two ways of getting my tails in your algorithm.